Today I'm talking about Dask and shared memory, as you know, and here's my outline. I'll be talking about Dask distributed in particular, and frame the question that I'm setting. What is shared memory? Why does it have any implications for Dask? And how I'm going to test it, and then show you some results, and then talk about where that leaves us. So let's get stuck in. Dask, lots of you will know what Dask is, but I'll give a very brief introduction for those of you that haven't heard of it before. So Dask is a Python library for parallel computing, and it enables you to work with a bunch of different high-level APIs, particularly data frames and arrays, most common, but other things too, like bags, which is generalized Python iterative functions, delayed for any kind of function calls, machine learning library. There's a whole load of different things that you can use with Dask, and what they end up doing is creating a graph of tasks that you want to execute, and those tasks are then executed by a scheduler. So you make your graph using normal data frame-like operations if you're using the data frame API, and then you say something along the lines of .compute. That will bundle up your graph. It will send it to a scheduler, and the scheduler will be in charge of executing that thing. And we'll be talking about the distributed scheduler here, in which case you're shipping the whole thing to a different process, and that control of how things get executed will depend on that process. Eventually, things will run on some workers and you get your results back. And because it's running on many workers, you get many times the CPU and memory than you would have in a single process. Here is a sort of logical layout of a Dask distributed cluster. You can see the client. The client is where you enter your commands, where you run your script or your notebook, whatever it may be. That's your client. Scheduler is the thing that decides when things run and where. And then the workers are the ones that actually run functions and produce results. So for example, and I put on some lines here. The solid lines are constant communication. So the client talks mainly with the scheduler talks to the workers talk to each other. Sometimes the client can fetch results directly from workers once those workers have produced a result, but that is the less common path. So here's an example. I've just filled in a few things on the background here. Let's say I've done some data framey thing, and the result that I want is the thing that the token key3 refers to. So key3 is some result. The client will say to the scheduler, hey, I would like to have key3, please. And here's the graph. And there you can see a simple representation of what a graph might look like. It says that key3 requires some function which is going to run on result key1 and result key2. Now, let's say that on your workers, you happen to have key1 on one of your workers and key2 on a different worker. In that case, obviously, if we want to run a function that depends on both of those, we'll either have to move key2 to be on the same worker as key1, or move key1 to be on the same worker as key2. And when I say work here, I mean copy. We're going to be copying and sending that data between workers. So we'll have redundancy, we'll have a duplication of however much memory key1 or key2 is using. Okay, so that's how Dask works in a nutshell. I hope that wasn't too fast for people. Again, I'm expecting that a lot of the audience here has actually used Dask, and this makes some sense to you. But I do want to have a little aside about deployment options for Dask, and there are many of them. And these are all Dask distributed deployment options. So in addition to the standard default Dask scheduler that works in a single process, you have a whole load of different ways in front of you that you can create a distributed cluster. You can have a cluster on a single machine. And in that case, you will be using each of your workers, and your scheduler and your client will be in different processes, but they will be on the same machine. And the most common way to do this is to use the local cluster. This is the same thing that you get if you just do client with empty parenthesis. Then you get a local cluster and it uses a number of workers on your machine, the number of workers depending on your CPU cores. But there's lots of different ways, and people use Dask in all of these different scenarios. So you might have access to supercomputing resources and be required to use a job manager, like these things that fortunately I don't have to deal with, but some people use these things. And you might be talking hundreds of cores or more. You might be using something that is more familiar to data scientists these days, some kind of container architecture, or Kubernetes, Yarn, maybe raw Docker, something else. And that something else might typically is then running within another framework. So your container providing framework might be in the cloud, it might be on premises. There's a whole load of different iterations that you might have containers. Each of those containers usually contains one Dask worker with one or a couple threads is typical. Then you might just have a bunch of machines. Again, you can do this very simply in the cloud, or you might have a bunch of machines in your lab or whatever it may be. And each of the machines runs one or more processes again, and there are various different ways to set these up. So you can, there are backends, so you could talk to the different cloud vendors, or you might just have direct SSH access to all of these machines. And there are managed versions of these, like Dask Gateway and other various commercial offerings too, where you get somebody else to create the cluster for you and you get access. So these have come with lots of great features. For example, if your CPUs are all busy, then maybe it will auto-scale provision more and more CPUs until you can manage the workload that you're dealing with. They come with various compromises. So startup time for creating a cluster from scratch might be fast or it might be slow, depending on exactly which one of these you're dealing with. And of course, whatever system it is, you probably have to care about how do you get access to the system, but nobody else, or how do you allow access to other people and all the usual enterprise things of auditing who does what where and who has permission to do these things. Now, I want to make one point clear, and this comes up in Stack Overflow. It comes up on the issue tracker. It comes up in all meetings that I ever have about Dask. The single most common thing that causes a Dask workload to fail is a memory error. One of your workers at some point is trying to use more memory than it is allowed to use, and it gets killed by the system, where system might mean the container, or it might simply be that just there's no physical memory available, and you get an exception. Either way, memory errors are by far the most common reason that a Dask workflow fails. So we really care about it. You have some options when you create these different kinds of clusters. These are the typical things that people will configure: the number of threads per process, the number of processes, how you impose memory limits, whether you spill to disk, whether you pause a worker until it has managed to churn through some of the backlog of tasks. The most common thing, or the easiest thing in many cases, if you are hitting a memory problem, is to get more memory, or more specifically, get a bigger machine that has more memory available and maybe distribute that across your containers or whatever it may be. I've highlighted GIL here. That's just to remind people that the choice between threads and processes in Python is very much dependent on the interpreter lock. So processes are good because they each have their own interpreter lock, so they can run efficiently in parallel. Threads are good because different threads can share memory, so you don't undergo the duplication penalty. Okay, so I've talked a lot about different deployment options. What about the case where you just have one single machine? Why would you want to do that? Well, there's actually quite a lot of compelling reasons for this. If you have a single machine, it's really easy to get Dask up and running. You don't have to worry about once you have the machine going, however you started that machine, all you need to do is start some processes. And that's as easy as having access to the machine at all. You don't have to worry about all these different frameworks for starting containers, for submitting jobs, for starting other virtual machines elsewhere and making sure that the networking between them makes sense. All of that is, well, it just disappears. It's easy because it's not even a problem. You just have to be able to access your machine. That means if you're going from absolutely nothing and you want to get going with a Dask cluster of reasonable size, you can spin up a machine in a cloud and have Dask running in pretty much seconds, depending on how you want to actually install Dask on that machine. It can be really, really fast. And these days, this wasn't always true, but it's been true for quite a long time. You can get some seriously big machines. So if you do have something that requires a lot of memory, you can get a lot of memory. It's not a problem. Get the machine, it starts up quickly, run your workload, close the machine again. It will not cost you that much money. It's probably cheaper in many cases than having a Dask cluster available on auto scale, so it's always there, even if it's always there on a relatively small scale. And having a machine that's twice the size, twice the memory, twice the CPU is actually twice the cost of having two machines of that original size. So the cloud pricing model makes this very much a tractable way to do things. And finally, and this is not very well appreciated usually, if you're running in containers and each container has 4 gigabytes of RAM, once you reach 4 gigabytes of RAM, you're stuck. You either have out of memory error or you spill to disk, you have to take evasive measures. You have to change your workflow, possibly, which is really painful. If you have a lot of processes on a single machine, they share the memory pool. It may be that some of your workers need way more than 4 gigabytes sometimes, but they don't probably all need a large amount of memory at the same time. So you can make pretty efficient use of memory like that and CPU. You can oversubscribe in this case. All right, so when processes talk to each other, this is the kind of very rough layout of how that happens. You have a process here, which contains some threads. You have a process here, which contains some threads. Each of these threads can see all of the memory within the process. But if you want to send data from one process to another, you're going to have to make some kernel calls, and you have to do some kind of serialization and transfer. Serialization might be over the file system abstraction, might be over the network abstraction, or there are other possibilities. In Dask, it almost always means TCP and network layer. And the reason is that this works equally well between processes on a single machine and between processes on multiple machines. So that's very convenient. But it's a lot of overhead. Also, it means that obviously, if you do that, you duplicate the memory. You had it in the original one, and you make a new copy in a new one, and you had to actually pipe those bytes between processes. As a counterpoint, shared memory looks something like this. Yes, you still have to make a call to the kernel at some point, but it's just going to allocate you some RAM somewhere in the system. This RAM can be made visible and in fact mapped into the memory space of multiple processes. So this dashed line here from process one's point of view, it looks like it's part of process one. It looks like it's just perfectly ordinary memory, but it in fact refers to this block of memory over here. And then process two has the same thing. It refers to this block of memory over here. So you don't copy the memory. All you have to do is make sure that the data you're interested in ends up here in this shared piece. And then all of your processes can view that memory with no duplication and no communication cost. It sounds like a really big win. Brief aside, there's a couple of mechanisms for making this happen. Classical shared memory, POSIX shared memory, and memory mapping. You don't need to worry about the difference. It doesn't make any practical difference for what I'm talking about here. Okay, so I thought for Dask, in the single node case, it might make a lot of sense to be able to not use TCP to send large amounts of data from one process to another, but to use this shared memory encapsulation. And here's a really sort of simplistic code snippet that shows how I did this. And there's links to the repos for those that are interested. This is my fork of distributed, where the actual code that does this, is located. And this is a set of benchmarks that show how well this did or didn't perform. Essentially what I'm doing is at the point at which Dask is ready to send data from one worker to another or from the client to a worker, we're going to pass it through Pickle and extract the memory views, the buffers from it. And each of those memory views, we're going to create a shared memory segment, and we're going to copy that buffer into that shared memory segment. Then we're going to remake the original object using those buffers and discard the original object. So we very temporarily duplicate memory as we do this copy, but then we drop the original object immediately. So now we have a new object that depends on these shared memory blocks instead. And those are what we pass off to the other worker, so it can also recreate the object based on those shared memory segments. I'm using 3 backends for comparison here: LMDB, Arrow, and Vineyard. Arrow is the one that's used by Ray. There's been a lot of discussion in Ray about whether they should switch to something else like Vineyard. I've put an asterisk here because Vineyard is, in theory, I haven't done this myself. It works inter-node, between nodes as well. So that might be interesting if you wanted shared memory and you wanted a networked thing, but that's not what I was investigating here. Okay, some things weren't done, and particularly Dask doesn't know that this happened. So Dask's metrics of how much memory is used where will be wrong. It will also not be aware that copying things from one place to another might be much faster than you think it is. And where should a task go, therefore, will be using the old system because it's a lot of work to try and change that. Okay, the results. So, and this is the only result side I'm going to show. I'm not showing you code, I'm not showing you live anything, and I'm not showing you tables. This is it. So I found, in short, that if you're scattering, this is whether you're scattering from the client to all of the workers or from one worker to all of the workers, but you are explicitly calling a replicate function. I want this piece of data to be seen by all of the workers. In that case, you get exactly what you expect. Instead of, let's say you have 6 cores, 6 workers, instead of having 6 times the memory footprint of the original object, you only have 1 times the footprint of the original memory object, and all of the other workers are able to just view that object without duplicating memory, without spending time on transfer. That's excellent. That's exactly what you wanted. However, on the other side, when you try and apply this to typical data frame and array workflows, and you can look in my repo to see what I attempted to do that would do this, I didn't get any improvement in those cases. These workflows are sort of overlappy, re-indexy kinds of things. So data is definitely being shuffled a decent amount, but we're not getting an improvement from shared memory. And finally, and this is a marginal result, LMDB was perhaps a little slower than the other two. It does have the different technology behind it. It maybe comes with better ability to spill to disk because it's a file system based one rather than a pure shared memory based one. I won't make much out of that because it's only marginal, not very important from this talk's point of view. Okay, so what's going on here? We managed to get a really good result, but in the workflow case, we managed to essentially not get a result. And the real reason that this happens, well, there's a couple of reasons. So I'll go through each of these and spend a minute talking about what these mean. Dask really tries very hard to assign work to the worker that already has the data that it's going to need for that task. That is, it does everything it can to reduce communication between workers and to reduce duplication of memory. This is actually in the very latest version of distributed, this is even more so the case. Memory management is even better than it used to be. So if Dask is trying to not copy memory, then having a way in which copying memory is more efficient than it used to be is not going to be as obvious or as important. A second point, and I mentioned this on the things that I didn't get around to trying or to developing, Dask's idea of how much memory a worker is going to need for a particular task, it will be wrong. And it's in fact quite tricky to account for shared memory because no particular process owns that memory. So and you can only release the memory when all of your processes are done with it. So it's difficult to say what's the cost of starting a new task that depends on some piece of memory. What's the savings from being able to release a piece of memory? Those things are now hard to reason about. So I didn't touch them. And Dask will be getting this wrong. It's going to assume that when you need a new copy of something that is already in shared memory, it's going to assume that you need that full amount of memory again. And Dask will not want to do it. It's also going to assume that the cost of transferring it will be the cost of the original serialization, where serialization meant copying it into shared memory. So it took some time in the first case. Subsequent copies are not going to take time. There is not an easy way in Dask to take account of this. And the third point might just be the most important one here. If you have something that is in shared memory and you take slices of it, on the Python level, you don't allocate memory, but you make a new memory view object. When you come to pickle this memory view object, you get a new buffer object. There is no way to know, or at least I'm not aware of a way to know, that this new buffer object is in fact part of a different buffer object that is in shared memory. In other words, with this new buffer object, we're going to make a new shared memory segment, even though the data of that buffer is already in shared memory. I don't know how to get around this. Maybe some people here know a way. Finally, and this is in practice what I might end up doing, we know it works well for scatter. In the case where we're explicitly replicating, there's a really obvious place that we can put this in. Ignore the serialization layer, just make an object that replicates itself using shared memory alone. That will be useful by itself. It's something that we can put straight into distributed, and it doesn't, you don't need to worry about the rest of these questions in that case, because it will be an explicit thing that the user knows they want to do. All right, coming towards the end now, here's a summary. I'll read through these because I think they're all moderately important. First thing is it's often overlooked that a single node workload is really important, whether you're doing it on a laptop or a big desktop, or you just have a single virtual machine with, hey, let's have 100 cores and 200 gigabytes of RAM. You can totally do that. And it's totally the right answer in many useful cases. And they come with some advantages that I went over before. I won't repeat myself there. But in particular, if you have something where memory is a problem, you can just get more memory for the workflow that needs it. You don't need to redesign your cluster. You don't need to go back to the drawing board and redesign your workflow and change your chunking schema, all those things. Sometimes it's the right answer. My experiments have shown that shared memory does what you would like it to do for when you're scattering specific data sets between your processes. That's good. But making it useful for data frame or array workflows, if it can be made to work, would require considerably more effort than I had time to do here. So the thing to take away here is either somebody wants to push this forward, but in practice, I'm going to make the shared memory thing available for scatter and replicate only. And then an open question to the people here from the Ray community. Ray has shared memory between processes. What do you do with it? How useful is it? How important is it? What happens if you turn it off? I would be very interested to know. Ray, of course, was the thing that brought shared memory to parallel processing in Python, at least to my notice, and that was the whole spur for trying to do this thing. So I'll leave it there, and we have about 5 minutes for questions. Thank you very much.
Thank you so much for your talk, Martin. Any questions from the crowd? Oh, oh, anything else you'd like to add, Mark? Oh, thank you, Carlos. No questions, but you are awesome. Yeah, I've gotten to know several of the Anaconda people over the course of the conference. Y'all seem pretty cool to me.
Thank you. This was fun and pretty much outside of my normal steam house, wheelhouse, whatever people say, and not the kind of work that I normally do. So they may well be the people who understand these underlying protocol things better than I do could have gone further, but nobody else was working on it in the Dask community, so I wanted to give it a shot.